Morning. So, what we're going to do this morning is do some more ordinal arithmetic, or examples from ordinal arithmetic. Perhaps using some of the exercises for this, but also there are still some lemmas left, the section that I want to do. I will say that do come to the problems class tomorrow, because I again will be doing more ordinal arithmetic exercises there. And I think this is will be good practice for you. I first wanted to talk about just kind of its way of recapping a bit and thinking about ordinals and ordinal suprema. So let me look at exercise 14 first. I mean, it's a slightly silly exercise in some sense because it asks the same thing twice. And it looks complicated, but it's really just something that's really straight from the definitions. So basically what 314 asks it says you have two sets of ordinals, x and y. And the point is that for every element of x, there's an element of y that's greater than or equal to it. And conversely, every element of y, there's an element of x that's greater than or equal to it. And you're asked to show that the supremum of x is the same as the supremum of y. So for every psi in x, right, there's a theta in y such that psi is less than or equal to theta. But also, for every theta in y, there is a zeta in x such that theta is less than or equal to zeta. Show that the supremum of x is the supremum of y. Well, solution. What is the supremum of x? It's the least ordinal greater than everything in x. So the least ordinal psi bar greater than or equal to every psi in x. It's also equal to the union. I'm sorry, yeah, it's the least, let's leave it at that. And supremum y is going to be the same thing. Least ordinal theta bar greater than or equal to every theta which is in y. So, okay, so there's a zigzag picture like this. Here's sup x and here's sup y. And somehow just the definition of what sup is going to tell us that these are the same. After all, what is sup x? It's the least upper bound of x. And sup y is the least upper bound of y. which is, after all this says here. But here, I mean, the picture kind of says it all. If I have something that's greater than or equal to everything in X, it's clearly greater than or equal to everything in Y, right? Because everything in Y is less than or equal to something in X. So I think you just say, but if tau is greater than or equal to everything in X, then let's label these things here 2 and 1, right? Then by 2, tau is greater than or equal to theta for any theta in Y. And similarly, if sigma is greater than or equal to everything in Y, so all this is saying is any upper bound for X is an upper bound for Y, and vice versa. Sigma is greater than or equal to psi for any psi in X. So the upper bounds for X and Y are the same, so the least upper bound is the same. So the least upper bound for X equals the least upper bound for Y. Hence sub X equals sub Y. So that's kind of a very full answer there about that. Are there any questions? Part 2 of the exercise just rephrases the question in another way. It's a little bit redundant, actually. I might cut that out for next year. Okay, following on from that was the recursion theorem, and I mean the definition of sup is a recursion theorem, definitions of ordinal arithmetic, and so on. So let's turn now to page 36. And I want to omit here lemma 342 and exercise 318. Right, so it's lines 1015 to 10036. Sorry, 8. No, sorry, 5. That's right. Okay, so let's skip over those. But I do want the corollary that follows, but we'll prove it outright here. So what does corollary 343 say? It's almost like saying there's subtraction and division for ordinals. So as I've got two ordinals, and they're non-zero, and alpha is less than or equal to beta. Then two things hold. So let's take them in order. There's unique ordinal gamma, so that alpha plus gamma equals beta. So this should be kind of intuitive after a while. Let's draw them going horizontally. Here's alpha. Here's beta. What the corollary is saying is that there's a unique gamma here that I can add on to alpha to get to beta. And actually, this just comes from the addition function. So proof of one. What is gamma? Gamma is simply that gamma so it's that ordinal I add to alpha to get to beta, which of course is just saying this picture in another way. Right? But you could sort of say, well, how do I know there's a gamma like this? Maybe the addition function hops over beta or something. Maybe it just misses beta out. So a more rigorous proof, right, would be to say, as the add alpha function is strictly increasing, right? So it's a function that's forever increasing like this. So this is saying if tau is less than sigma, then alpha plus tau is less than alpha plus sigma. Or writing it out in the formal definition way. So these alpha plus taus, these are strictly increasing. Then we can look at the class Z, right? This is the collection of taus such that alpha plus tau is greater than or equal to beta. Then Z is not empty. Sooner or later, alpha plus taus are going to exceed beta, right? And the gamma we want is the least element of zeta. Then gamma is the smallest element of zeta, right? I mean, you might still then be worried and then say, but what if maybe alpha plus gamma is bigger than beta? Since if alpha plus gamma is bigger than beta, either gamma equals delta plus 1, either it's a successor or a limit. But gamma is the minimum thing in Z. Right? So alpha plus delta is less than beta. But then this is nonsense. alpha plus delta, alpha plus delta plus 1 is alpha plus gamma, right? And that's less than or equal to beta. If I add 1 to this, I end up being less than or equal to beta here. But alpha plus gamma is supposed to be bigger than beta. That's a contradiction. So the two cases, if gamma is a limit, then alpha plus gamma is by definition the supremum of the alpha plus deltas for delta less than gamma. Just using the definition of a alpha here. But now we're supposing this is bigger than beta, right? So this here is supremum, is the least upper bound of all of these ordinals that are here. So if this ends up being beta, there is something in here that ends up being greater than or equal to beta. If alpha plus gamma is bigger than beta, then there's delta less than gamma, so that alpha plus delta in this set here is greater than or equal to beta. Again, contradicting the fact that gamma is the minimum element of Z. So that's a rigorous proof in glorious detail, right? That I can always find for two ordinals like this, something to add on to this to get to that, right? In terms of addition. Okay. So that's part one of that. I don't know if there are any questions yet before I do part two. What does part two say? There's a unique pair of ordinals, and I call them psi and eta. So it's the same picture as above. Alpha is less than or equal to beta, bigger than 0. So now what I'm going to say is that beta, I can think of it as so many multiples of alpha plus a remainder, right? Just like a kind of division algorithm. So there's a unique pair of ordinals, psi and eta, so that I can think of the larger beta as psi multiples of alpha plus this remainder. So this is a sort of quotient, and this is a remainder. And the argument is going to be pretty similar to part one, right? Okay. So let's see how that goes. So what do we have? 0 less than alpha is less than beta, and we want psi and eta so that alpha lots of, or psi lots of alpha plus eta equals beta. So here's alpha, here's beta, and I'm going to have to keep putting in multiples of alpha in here. So they're going to be psi of these. But of course, it may not go exactly. There's going to perhaps be some leftover eta. So that's a picture. Yeah. So again, we use now the fact that multiplication is increasing. So beta is always less than beta lots of alpha. Alpha is at least 1, right here. And this is, sorry, strictly less than. Right, so the strict increasing, as we're saying here, this is alpha times beta, and this is alpha times beta plus 1. So I would have done better to choose a different letter than beta in here. Let's call these beta bars. It's not supposed to be the beta of the of the question. So now again, I choose then the least psi or beta bar so that alpha times psi is bigger than beta. So I can phrase it slightly differently from part 1. Alpha times psi is less than or equal to beta, but alpha times psi plus 1 is bigger than beta. Sooner or later, there'll be a multiple of alpha, which I lay out along here, and it'll overshoot, it'll go beyond beta. And then as psi increases, more multiples get yet bigger. So by rules of ordinal arithmetic, this is just the same as alpha times psi plus alpha here. Now I apply part 1 with alpha times psi in place of alpha. So part 1 will say, right, there's a unique eta such that I add eta to this, I get beta. It's called gamma in part 1. Alpha times psi plus this difference is beta. It might be 0 if alpha times psi happens to equal beta. So that establishes that I've got at least one pair psi and eta that work. one pair xi and eta. To satisfy the lemma. Well, again, it's called corollary in the notes. But the corollary says there's a unique pair. I want to make sure there isn't another pair like this. So suppose psi prime eta prime is another such pair. And we'll show that these equal psi and eta. So if xi equals xi prime, then alpha times xi is the same as alpha times xi prime, obviously. But then beta, which is supposed to be alpha times xi plus eta, is the same as alpha times xi or xi prime plus eta prime. But part one again said there's a unique eta that I add to anything to get something else. So part one gives us that eta is equal to eta prime. And part one said there's only one thing I can add to an ordinal to get another one. So this was under the assumption that xi equals xi prime. So all we have left is to show that xi equals xi prime. So we have only to show xi equals xi prime. Okay, so let's suppose they're different and one is less than the other. Suppose it's that way around. Xi plus 1 is then less than or equal to xi prime. So how can I express beta now? Beta is alpha times xi plus eta, because we suppose xi and eta are good. But this is less than alpha times xi plus alpha, because remember, eta is the remainder, right? It's the bit that's left over that I need to add on to this multiple of alpha to get to beta. So I'm using that eta is less than alpha and that the adding function is strictly increasing. So those are my reasons for that strict inequality here. But now I use some ordinal arithmetic and I say this is the same as alpha times xi plus 1 here. But xi plus 1 is less than or equal to xi prime. Again, I'm using this. And I'm using that the multiply by alpha function is increasing. Well, again, this is less than or equal to alpha times psi prime plus eta prime. I don't write strict less than because maybe eta prime is 0. But in any case, even if it's 0, I've got a contradiction because psi prime and eta prime were also supposed to work and give me beta. But now I've got beta less than beta. So this is a contradiction. So this supposition here is wrong, and psi equals psi prime. So and that finishes that corollary. Any questions? Okay, let's look at say 319. Because it's illustrating the same kind of approach. Suppose I've got only alpha less than omega cubed. Then there exists unique natural numbers, nk and l, such that alpha is n lots of omega squared plus k lots of omega plus l. Okay. So we use the same kind of reasoning as before. I'm not trying to find a multiple of omega. I'm trying to find a multiple of omega squared. But then there's perhaps some stuff left over, right? Maybe that stuff that's left over I can think of as a multiple of omega plus some further stuff left over. So that's the approach. So some multiple of, well, the largest thing there. Plus some remainder rho. Okay, so then think of rho as, well, it's no longer multiples of omega squared because we've exhausted those. Plus some further remainder. R, right? Because it's some remainder after we've taken out multiples of omega, this will be a natural number. Well, it's the L that's up there. Okay, so in square brackets, that's part of my thinking, right? It's not, it doesn't have to be part of my answer. Right? So, as in the last proof, so as in the proof 2 above, what we'll do, let n be least. so that alpha is less than too many multiples of omega squared. So I'm thinking here of, well, again, also aside, what am I thinking? Omega cubed is omega squared times omega. And multiplication function, right? So this is m omega squared times omega. So this is a limit case here. So this is, by definition, the supremum of the omega squared times n's, for n less than this limit ordinal. So, and here's my ordinal line growing out this way. Here's omega times 2, and so on. Here's omega squared. Here's omega cubed. And omega cubed is the supremum of these omega squared times n's. So alpha is less than omega cubed, we're told. So alpha sits somewhere here. Right. Alpha is less than omega cubed. So for some n, I'm going to have omega squared times n is less than or equal to alpha. And omega squared times n plus 1 is too far. Okay, so omega squared times n plus 1 there is too far. What is this? I mean, this here is omega squared times n plus omega. And this is omega squared times n. And here, this is the result of going omega squared times n plus 1, plus 2, plus 3, plus 4, and so on, right? Sorry, omega squared times n plus omega squared. So altogether, this multiple of omega squared is too far. Now again, omega squared, just to spell it out, is omega times omega. And this is the supremum of the omega times k's for k less than omega. So omega squared times n plus omega squared is too far. So there's going to be some least k, such that omega squared times n plus omega times k is going to be too far. So now pick k less than omega, so that alpha is less than omega squared times n, right, plus omega times k plus 1. But omega squared times n plus omega times k is less than or equal to alpha. I don't even need to write this bit down, right? I'm just analyzing what happens when I go too far. Okay, so this here, this is omega squared times n plus omega times k plus omega. So again, this is a bit too far. Whereas this is less than or equal to omega, so less than or equal to alpha. So this is the result of just adding 1, adding 1, adding 1 onto this. So after I've added 1 sufficiently many times, L many times, I get alpha. Now to L be least, such that omega squared times n plus omega times k plus L is alpha. So again, using part one of the last corollary, given an ordinal less than alpha, I can find something to add to it to get to alpha. So by part one of the last corollary, if you want. So with some practice, and I do urge you to get practice, these things will become a little bit more familiar, I think, to you. Any questions there? Okay. And let's look at some of those laws of arithmetic. So this is going to be very similar to the arithmetic on the naturals. So let me just, I won't write them out, but let's just look and see what they say. So you can see they're just the associative law for addition. There's an associative law for multiplication down here. There's a distributive law of multiplication over addition here. And here's an exponential rule, right? Alpha to the power beta plus gamma is alpha to the power beta times alpha to the power gamma. So with natural numbers in place of nk and L, these are unproblematic, and we've already seen how to prove them, right, in the last chapter. And we prove them exactly the same way, except that here we've got, you know, ordinals come in three flavors. So we have to deal with a limit case, right, which is then slightly different, well, which gives an extra case, right? And again, as I said, a hint for proving these things is do induction on the last variable that appears. So all of these, there are three variables, alpha, beta, gamma. Do the induction on gamma here. So let's just go through. Let's just go through these. Although yes, I see. Okay, I use the last exercise there. Let's see, how's the time going? Let me do the last exercise and then finish for today. 321. Let me do B. Set of ordinals without a largest element.
I'm not sure why, but it's not
I'm
focused.
sorry. Thank you. Okay. Okay. So here's X growing upwards. show that, well, alpha plus sup x is sup x. Right? There's no largest element in x, so the elements of x go unboundedly up below this least upper bound, sup x. So this is supposed to be the sup, or the least upper bound then, of the alpha plus tors for tor in x. And similarly for the other operations. Alpha times tor and alpha to the power tor. Okay. Okay, so this is 1 to 3 of that exercise. Okay, so how would this work? So maybe I have time to do one. Let's do part 1. So let lambda be the supremum of x. We're told x it has no largest element. So lambda is the supremum of x, but it's not a member of x. So we make some observation. If I've got any sets of ordinals, one is a subset of the other. Then the supremum of the alpha plus tors for tor in x. This is less than or equal to the supremum of the alpha plus tors for tor in y. Nothing fancy there. There are simply more things in y than there are in x. So this least upper bound can't be any smaller. So x is a subset of lambda. Lambda is its supremum. Here was x. Here's lambda. So every element in x is less than or equal to some element of lambda. So as x is a subset of lambda, the sup of the alpha plus tors for tor in x is less than or equal to the sup of the alpha plus tors for tor less than lambda. But this is by definition. Sorry, this is alpha plus lambda. Because x has no largest element, lambda is a limit ordinal. And I'm just using the definition of alpha plus lambda when lambda is a limit. I'm trying to show that this supremum equals this, right? So we have one direction here. It's less than or equal to it there. So now I'm going to say as the add alpha function is strictly increasing, if I've got tor less than tor prime, then alpha plus tau is less than alpha plus tau prime. But what do I also have here? Sorry, what do I want to say next? I want to say that everything is, so any tau less than lambda is less than some tau prime, which is in X, right? Lambda is the supremum of the things in X. Pick any tau here, there's a tau prime in X that's greater than or equal to it. So any alpha plus tau from a tau from lambda is less than an alpha plus tau prime from a tau prime from X. So again, supremum of the alpha plus taus for tau less than lambda is less than or equal to the supremum of the alpha plus tau primes for tau prime in X. And again, this is alpha plus lambda. So I've got I've said more or less the same thing twice, but that gives me the inequality in both directions, right? The supremum is less than alpha plus lambda is less than or equal to the thing in question. So that finishes that part one. And the multiplication and exponentiation is pretty much exactly the same. You just replace plus by times, and instead of saying addition is increasing, you say multiplication is increasing or exponentiation, and then replacing all of these pluses by times it's pretty much verbatim. Okay, so we'll use that exercise to perhaps next time I'll do that next lemma using this exercise. Okay, are there any questions there?